In previous videos in this chapter, we've been looking at experiments that pointed to the fact that we didn't have a complete understanding of nature back in the early 1900s. One additional experiment that is really important in the development of quantum mechanics is what's known as the hydrogen emission spectrum. This is a figure from your textbook that shows what this might look like. And essentially what we're looking at here, we have a few different elements here, but we're talking about this one on the top here. This is a bunch of hydrogen atoms that are inside of a tube, kind of like a neon light. That's what's shown here on the left over here. And if you send electricity through those hydrogen atoms, they will emit light. And so what we're looking at here is, in this section right here, this is the emission spectrum. So yet again, this is another experiment involving light that tells us about quantum mechanics. So that's why we had to cover and talk about light. And we can see along here at the bottom we have different wavelengths that are represented. So this is what we call a spectrum, meaning we're seeing how much light we get out of this system, in this case hydrogen atoms, depending on the wavelength. And what we see from hydrogen, and not just hydrogen, also from helium and neon that are below, though they get more complicated for helium-neon. For hydrogen, we see a very clear, distinct set of peaks. And so each of these peaks is separate. Unlike if we look at the light from the sun or from, for example, an incandescent light bulb, we see light from all the different colors represented. But with hydrogen, we do not see that. And this was something that puzzled scientists. And sort of over the course of decades and even, probably over a century, people worked on this on and off. And the scientists looking at this, some of them not even like full-time scientists. One of the first was a school teacher. Anyway, different people looked at this and tried to puzzle, why did it look this way? What were the relationships between these different wavelengths that we observed? And so one of the first things that was discovered by Johann Balmer in the 1885 was that you could write an equation that could predict for these lines that we see here, the visible lines. You multiply it by a constant, and you can come up with some numbers here, m squared over m squared minus n squared. So he discovered that if you can take this set of lines and it fits this equation that he came up with. And n is equal to 2, n has to be equal to 2, and then m is equal to something bigger than 2. And by doing that, you could predict where all these lines showed up, and you could even make the prediction, which Balmer did, that maybe you might have something where n equals 3. Right? Have a different set of lines, and those would show up at a different wavelength. And that actually does happen. So all we're looking at here are the visible lines, but there, as you keep going further this way into the infrared, at longer wavelengths, there's a whole other set of lines that come from this equation, but using n equals 3 instead of n equals 2. And so different people discovered different sets of lines, and eventually Johannes Rydberg, around in the late 1800s, came up with an equation that described all the lines. And this is only for hydrogen. So this does not explain helium, this does not explain neon, but hydrogen's a relatively simple spectrum, but even then, scientists were a little bit puzzled. And one thing that maybe should jump out at you, is that the fact that we have integers here, right? These are integers, n2 and m something bigger than 2. These all have to be whole numbers. Similar to how Planck had to include integers in thinking about quantized energy in explaining blackbody radiation. We're seeing the same thing show up again. Quantum mechanics is at the heart of what's happening here. And so a more generalized equation is the Rydberg equation, and this works for any set of lines in the hydrogen spectrum. In fact, you can still use this equation is still used sometimes today. So Rydberg plotted things in terms of 1 over wavelength, a unit that I use a lot called the wave number. And we have this constant 1.097 times 10 to the minus 2 nanometers to the minus 1. So because this is 1 over wavelength, we get units of 1 over distance. And then we have a slightly, just a rearranged version of this one up here, 1 minus n1 squared minus 1 minus n2 squared. And this is the Rydberg equation that describes the emission or absorption spectrum of hydrogen, meaning the light that's given off when we send electricity through hydrogen. It doesn't work for helium, doesn't work for neon, but this does work for hydrogen. And let's explain real quick. So this constant is just a constant that he saw fit the data, but the numbers here, n1 and n2, n1, let me make sure I get these right, n1 is a positive whole number, and n2 is equal to n1 plus 1, n1 plus 2, etc., etc. So it's bigger than n2, kind of like our n and m previously for just looking at the Balmer series. Okay, so we have this equation that describes what's going on with hydrogen, but it doesn't explain why that's what's going on with hydrogen. This was just fitting to the available data. This is what we call an empirical formula, meaning kind of like our idea of an empirical chemical formula, meaning it just comes from observed data. But there's no underlying theory that explains why we would see this trend and why it would depend, specifically this part, why it depends on integers, these whole numbers. So in the next video, we'll look at the first model that was able to successfully explain this spectrum observed for hydrogen, which is the Bohr model of the hydrogen atom, which, while not being completely correct, has a lot of fundamental ideas that show up in quantum mechanics.